In this video, I will be using the integrated development environment Vivado from the manufacturer Xilinx to demonstrate the typical design flow when designing circuits for FPGAs. To refresh your memory, I will briefly go through the typical design flow when designing circuits for FPGA. We start with the design entry, where we can use VHDL, for example, to describe our circuits. We then perform simulations to verify that the circuit behaves as intended. After that, we run the synthesis, where our description is translated to gate level, or something that is available on the target FPGA. Then we run the implementation. Now all the resources get placed in the FPGA, and all the routing is done within the FPGA. After this, we can do another simulation where we also will see all the delays of signals. And we can then analyze if all timings are met in the design. Lastly, we program the device and perform testing on the FPGA platform. All manufacturers of FPGAs also supplies electronic design automation tools to help you in the design of circuits for FPGAs. In this demonstration, we will be using Vivado from the manufacturer Xilinx. Vivado is an integrated development environment that has a graphical user interface for the electronic design automation tools. This is the circuit that we will be used in this demonstration. So the circuit consists of 3 gates, a NOT gate, an AND gate, and an OR gate. It has 3 inputs, A, B, and C, and the output Q. We also have the truth table for this circuit to the right. Our target device is an FPGA named XC7A100T CSG324-1 from the manufacturer.
So this is the startup screen of Vivado. I use version 2016.1. It's quite old now, but in the new version you will find similar features as I will show you. So we will go ahead and create a new project. Then we will get this wizard for a project setup. We will name this project My System. And then we need to specify which kind of project we would like to create. So there are different options here. We will stick with this one, RTL project. So here we can add sources and then let Vivado run synthesis and implementation and so on. And we will not specify sources right now. We'll do it later on. So we click next here. Then we need to choose our target FPGA. So I will be using Arctic 7, and the one I use has the package CSG324, and the speed grade for this device is -1. So this is how fast this FPGA is. So they come in different flavors here. Some are slower, some are fast. So down here I find the XC7A100T CSG324-1. So this is the FPGA I will be using. Here we also have a lot of information about this FPGA. It has 324 IO pins, or pins on the chip. It has some random access memory that we can use. It has some DSPS, which is digital signal processor slices. It has quite a lot of flip-flops that we can use. This one doesn't have any gigabit transceivers. It has 120 IOBs, which is where we can connect to other things in our system. It has around 60,000 lookup tables. It has a PCI Express interface. And then we have some additional information about maximum temperature and voltage. Okay, so we go ahead with this one. And we get a summary. So we just click finish. So this is the startup layout of Vivado. And here to the left we have the flow navigator, and then we have project manager, IP integrator, simulation, RTL analysis, synthesis, implementation, program and debug. So this is the similar to the design flow I showed you earlier. So we have like the different steps here. So we will start with adding a source. So we will create a new design source. We put here. We will call this module my logic, and we will be using VHDL. There are other options available here as well. So we hit OK and then finish. So now we'll just input some things here. This is the port of this circuit or module. So it has 3 inputs, A, B, and C. And then we have 1 output, Q. So now Vivado will create a template for us, a VHDL template. And don't worry too much if you don't follow the syntax here. We will cover it in later lectures. So the file we added will appear here under design sources. So we can go ahead and open this one. And then we have the VHDL source code for this module or circuit. So we will cover this part later on, but I think you can follow what I'm doing here anyway. So down here I will specify how the output is generated. So Q will be not A or B and C. So it's the same. This is just a logic expression for this signal Q. Okay, so that's it. I will just go ahead and save this file. And once you save things, Vivado will check for syntax errors, and you will get warnings down here if there are any things that you need to correct. So now we can let Vivado analyze our code and see what it interpreted as by using this RTL analysis. So we click on Open Elaborated Design. And then we can click the schematic here. So here we see it. We have 3 inputs, A, B, and C. We have the NOT function here, this circle. We have the AND gate, the OR gate, and the output. So this is identical to what I showed you before. Okay, so next step, we will run a simulation. But to do this, we will need a test bench that generates input patterns here to our circuit. And then we can observe the output Q. So we will go ahead and add another source. But this time we will add or create a simulation source. So we choose this one. We name it my logic TB. We click finish. And we can just click OK here. So now you can see the file that we just added, it doesn't appear under design sources, but under simulation sources we now have 2 files. So here is the one that we just added. So things that are under design sources are the ones that will be used for generating hardware. And down here we only have things that will be used for simulation. So let's go ahead and open this one. Now I have already written this test bench code, so we'll just copy paste it. And we will also go through how you can write test benches in later lectures. But basically here we connect our circuit my logic to this test bench. So we connect A to ATB, B to BTB, C to CTB, and Q to QTB. And then we generate inputs. So here we have 0, 0, 0, and then we wait for 10 nanoseconds. Then we have 0, 0, 1, wait for 10 nanoseconds, and so on. So in this test bench, I have just listed all possible input patterns. You can do this other ways also, of course, with the loops and other things. Anyway, so let's go ahead and save this file as well. So now you can see here under simulation sources, now we got a hierarchy here. So since the test bench uses our circuit, my logic will be listed under this one. Okay, so this simulation requires 80 nanoseconds to complete. So I will just input this here in the settings. And then we can run this simulation. So run behavioral simulation. So now it's done. So for this demonstration, we'll just take a look at this wave window here, where we can see the value of all our signals. So let's zoom out here. So QTB is the output of our circuit, and we can see here that as long as A is 0, the output is 1. And then when A is 1, the output only becomes 1 once B and C are 1s back here. We can also check another thing. So let's go to this falling edge of the output. And let's zoom in. So here we can see the simulation step, quite small step size. But the thing that I would like to show you is the thing here, that as soon as the input change, the output changes immediately. So there's no delay or information about delays here. This is just a simulation that is performed on our description that we have given to Vivado. Okay, this looks quite okay to me. So let's say we are done with this simulation. Then we can go ahead and run the synthesis. So we click this button here. And this might take some time, depending on the size of your circuit that you have described. So it's done, and now we can do other steps, but I will skip this. So what we can do now is we can open the synthesized design here. And now we can take a look at the schematic. So you might remember this from the RTL analysis. We had this schematic. We can also view the schematic after synthesis. So let's check this one. So you can see now we don't have any gates anymore. Instead we have this lookup table here. And we have that A is connected to I0, B to I1, C to I2. And if we use this one, we can also view the truth table for this lookup table. So this is actually the same as I showed you earlier. We can also view the LUT equation here. So I0 is A, so this is not A, or I1 and I2, that is B and C. So this is the same expression as we input in the description. You can also see that Vivado has added some buffers here at the input and the output. Okay, so before running the implementation, we can apply some constraints on this design. So we can start with checking the input-output ports. So we have some scalar ports here. So here are our inputs and output. And right now they are not configured here, so they have not been assigned a specific package pin. So we can click on the package. And this is a view of the actual FPGA chip, where all these gray dots are pins on this chip. So what we can do now is that we can take this A and we can drop it where we would like it to be. And the location here is highly depending on how the printed circuit board for this FPGA looks like and how things are routed on the PCB printed circuit board. Here I will just put them in the corner here. As you can see, you get some pins here. And then we also need to specify which voltage level standard which you use for this logic. So I will just go ahead and choose the default. This also depends on what is connected to these pins on the printed circuit board. Okay, so now we need to save this constraint. We get some warnings here. We need to create a constraint file. So we call this my logic constraint. We can also apply some constraints on timing. So let's do that. Oops, wrong button. So we edit timing constraints. So if we don't do this, we will not get any information about how fast this circuit is. So we will just specify a maximum delay here. And then we choose where Vivado should calculate this delay from, the starting point. So we choose IO ports, find, and then we choose A, B, and C as the starting point. And the end point, here we choose the output Q. Okay, and then we set, let's set a quite high value here, 20 nanosecond. This is just for demonstration purpose. We hit OK. Then once again we need to save this to our constraints. And all these constraints will be stored in a file here that we can view. So here we have the my logic constraint. And here we can see we have this where we connect the pins to which package, or how we connect our ports to the package pins, which voltage standard we use, and then we have this constraint for the maximum delay of 20 nanoseconds. Okay, so now we need to rerun the synthesis after this. Okay, we are done. So then we can go ahead and perform the implementation. At this step, all the resources will be located somewhere in the FPGA, and all the routing will be done in the FPGA. So before running this, I would just like to show you here that you can, for both synthesis and implementation, you can apply different optimization techniques. So here's a quite extensive list that you can choose from, and if you would like to use this, you really need to read on what they mean. Okay, we'll stick with the default here. So let's run the implementation. So the implementation is completed, and we can go ahead and open the implemented design here. So we have got some warnings. Just check this one. Okay, this one we can actually skip. It's just that you only input the maximum delay, not the minimum delay, but that's okay for this demonstration. So what we can do now is that we can get the timing summary, and if we go down here, we have this is the one that we specified. So this is from A to Q. We have a total delay of 6.7 nanoseconds. And we can see that the lookup tables contribute with 3.7 nanoseconds and the wires within the FPGA approximately 3 nanoseconds. And in this case, we meet the requirement of a maximum of 20 nanoseconds. So that's good. We can also take a look inside the device here. So this is all the resources that are available inside the FPGA. So we can see here our output Q. Let's mark everything here. Maybe hard to see, but it highlighted some things down in this corner. So this is where our design is placed by the design tool. So if we zoom in here, we can see these purple things here, or pink, are the input output ports. So we have some inputs and one output here. The white lines here are the connections that have been performed by the tool. So if we zoom in this area down here, we can see that this is connected to a 5 input lookup table here. So if we click this one, we can also view the truth table of this one, and we can view the LUT equation. It's the same as before here. So this is where our logic has been implemented, and then we can also see the connection. You can also see that there are a lot of other things available in this FPGA. So this is what is called a slice, and you can see that we really had quite a lot of these things available for designing digital circuits in this FPGA. And this is I would say mid-range FPGA from Xilinx. Okay, so what more can we check now? We can check the utilization. So we can choose this one, project summary. So down here we have the utilization report. We can choose the table. We use one lookup table. We have some more available. We use 4 IOs. We have some more available. We can also see the total power that our circuit consumes and the operation temperature and so on. There are also other things that you can get, like noise and as well as other things. So before we continue, or more precisely the next step would be to run another simulation. So we will now perform a post-implementation simulation. So we choose this one. And this simulation typically takes a bit longer time than the one that we performed earlier. So let's close this one. It's same as before. We have this wave window here that shows the inputs and outputs. We still use the same test bench for generating input patterns. So if we zoom out here, you can see that it performed like before. But we didn't get any information about delays here. So what we need to do is we need to run a timing simulation. So as you can see now, things are starting to happen here. So for example here, if we don't even need to zoom in here. You can see that here at 40 nanosecond the input pattern changes, but it takes some time before the output changes here. So this is the delay caused by lookup table and wires and input output buffers in our FPGA. You can also see that we will get a glitch here, and this one is probably caused because here the C and B the input, this is the input to our circuit, so they are 0, 0, 1 here, and then the opposite. But because of delay, this C signal will stay high for some time in the circuit, and then this B will also be high, and at some point they are actually high at the same time, and this will generate this glitch here. So there's a lot of things to think about when you design hardware, especially for higher speeds. Okay, but anyway, we can live with this. Let's say we just sample at some other time. So the last thing to perform now is that we need to generate the bit stream, which is the configuration for our FPGA configuration file. So we click on this generate bit stream. Okay, it's done. Then we can open the hardware manager. So this is where we connect to the FPGA. So now I need to plug in the FPGA to my laptop and power it on. So I will perform that. And then I click this open target. And let's use the auto connect here. So here it found my FPGA. So this one. And then we can program this device here with the bit stream that we just created. So we just hit program here. Okay, and then we just need to test the device and see that it performs as we intended. It is also possible to debug the FPGA by inserting probes, and then we can view the signal value in real time in Vivado. And the last thing, as you can see, there are quite a lot of things that you can do. So these tools for designing with FPGAs are really very complex with a lot of things that you can change and control. But if it's also possible to do quite simple designs without getting into too much details here. Okay, so let's finish this demonstration.